Hi, so today's problem is actually quite a simple one. So the problem is if I have a top and I put a spin on it, the top stays upright, yeah, almost. But if I have a pencil and I've got a nib on it, obviously, then the pencil seems to fall down almost immediately. So why this difference in motion between a pencil and the top? Now, one thing that is directly obvious looking at the two bodies is that the diameter of the top is much larger than the diameter of the pencil. So maybe that's got to do with something, but how? So that's the problem. Now, there's something known as the gyroscopic effect that basically gives the reason of why a top spins in the first place. And that is what we'll be investigating. But before I talk about the gyroscopic effect, I'd like to speak about torque, which is the basis of the gyroscopic effect. So let's talk about torque. Now, a lot of you will know what torque is. Anyway, there are a few things you may not know. So torque is the equivalent of force, but in circular motion. So all of you may know this formula that if I have something rotating, this is the center of rotation, this is the force being applied, and this distance between this distance is called as R. This is the distance between F and the perpendicular distance between F and the center of rotation. The important word is for perpendicular. So torque, which is denoted by tau, is equal to F into R. Now, what that basically means is that, let's say I've got a wrench, okay, and yeah, there's your wrench, and I need to make this spin. I could apply the force in this first point or in the second point. R1 is obviously lesser than R2. So to spin this wrench by the same torque, I'd have to apply a much greater force in the first region. So F1 would have to be much greater than F2 if R1 into F1 were equal to R2 F2, you know. So it's much better to apply a force towards the end of the object, so you'll get much more torque. If you've seen doorknobs, those are the hinges. I'm just going to draw the door. Okay. If you've seen doors, then the doorknob is always towards the end of the door, so that there's maximum R. You know, if the doorknob is somewhere around here, it might in fact be impossible to open a door because it'll be too close to the center of rotation. So now something else that is important as well. Let's say that my force wasn't acting perpendicular to the point. Let's say it was acting at a certain angle, and the angle between the line going towards the center and the force is theta. Okay, then what would be the torque? Okay, so now we need to find out the distance between the center of rotation and F that is perpendicular. So we will project this F backward. We'll draw a line perpendicular. This is our new R. And how do we mathematically find R? We take theta, yeah, vertically opposite angles, and now this R will equal to, this new R will equal to the original R into sine theta. You can check this out, it's simple trigonometry. So now tau is actually equal to F into R into sine theta. So what this means is that if I have a force that is acting perpendicular, sine theta would be 90 and sine 90 would be 1. So torque would be maximum. However, if the force would be acting along this plane, would be acting towards the center or away from the center, then sine theta would be 0. And what that means is that there'd be no torque. And in short, there'd be no circular motion. Which makes sense that if I hit this object right towards its center, why should it rotate? There'll be no, there'll be no flicking in this direction or this direction. So that's how torque is calculated. But I said earlier that that's not it actually. Torque is the equivalent of force, and force is a vector. That is the exact same reason why torque is a vector as well. So you'll see many videos where people tell you that to find out the direction of torque, you use the right hand rule. What that means is that if I have something rotating in the anti-clockwise direction, how will I find out torque? So I will simply curl my hand, my fingers in that direction and point upward and stick out my thumb basically. So it's in this direction, this is the curl, and I take out my thumb towards you, towards the camera. So my torque, is actually acting upward, out of the paper. I cannot draw an arrow, so I'm just going to write outward. Now, if the motion was clockwise, it would be the opposite. I have to put my fingers this way and point downward. Okay, you can try it out yourself. So it would be inward. Now, what if I were looking at a disc sideways? I'm looking at it from the side, and the motion is in this direction. Yeah? So I curl my fingers and I point towards this way, this way. My torque